When Richard Feynman spoke about magnetism, his first keynote idea was quietly radical. Magnetism is not a separate, mysterious force that exists on its own, but a visible outcome of deeper electric and quantum interactions. At first glance, this sounds like a technical clarification, but when followed carefully, it dismantles how we instinctively think about forces, causes, and even reality itself. From childhood, we are trained to divide the world into categories. Gravity pulls things down, electricity shocks. Magnets stick. Each seems like its own independent actor, operating with its own personality. A magnet attracts iron. That feels like a complete statement. But Feynman insisted that this way of thinking is a shortcut, not an explanation. It satisfies curiosity at a surface level while hiding the deeper structure underneath. Magnetism, he argued, is not a standalone phenomenon, but a consequence of how electric charges behave when they move and interact at the smallest scales. To understand why this matters, imagine how we usually explain physical events. If you drop a stone, you say gravity pulled it down. If asked why gravity pulls it down, you might say because of mass. Press further, and you may mention space-time curvature. Each step feels like progress, but eventually you reach a point where there is no more familiar language left. Magnetism reaches that boundary faster than most forces, because it tempts us with everyday objects while being rooted in profoundly non-everyday physics. Inside every magnet are atoms, and inside those atoms are electrons. These electrons possess electric charge, and electric charges create electric fields. That part feels manageable, but electrons also possess a property called spin, which is not spin in the ordinary sense of something rotating through space. It is a quantum property with no classical equivalent. Yet this spin behaves mathematically as if it creates a tiny magnetic field. When many electrons in a material align their spins in a coordinated way, their individual magnetic effects add together. What you experience as magnetism is this collective alignment expressed on a human scale. This immediately dissolves the idea of magnetism as a separate force. There is no magnetic substance flowing between magnets. There is no magnetic glue. What exists are electric charges, quantum rules, and fields that permeate space. Magnetism emerges from these ingredients, the way a wave emerges from countless moving water molecules. The wave is real and powerful, but it is not a new substance added to the water. It is an organized pattern arising from deeper behavior. Feynman emphasized that calling magnetism a force is convenient but misleading. It is convenient because it lets engineers design motors and physicists write equations. It is misleading because it suggests something fundamental and independent. In truth, magnetism is inseparable from electricity. Together, they form a single framework, electromagnetism, what we label as magnetic. Effects are simply what electric forces look like when charges are in motion, or when relativistic effects come into play. This is where reality begins to feel unstable to our intuition. If you are standing still relative to a charged particle, you may observe only an electric force. But if you move relative to it, magnetic effects appear. Magnetism, in this sense, depends on motion and perspective. It is not an absolute feature of the universe in the way we imagine solidity or weight. It is a relational phenomenon tied to how observers move through space and time. Feynman loved pointing out how unsettling this is. Two observers, moving differently, can disagree on how much of an interaction is electric and how much is magnetic, yet both will predict the same physical outcome. The distinction between electric and magnetic forces is not carved into reality itself. It is a human categorization layered onto a deeper, unified structure. This means magnetism is not a thing but a description, a way of carving up a more fundamental interaction for convenience. At the deepest level, what governs magnetism are equations. These equations do not explain themselves. They do not say why they are true. They simply work. They predict with astonishing accuracy how charges and fields behave, how magnets attract and repel, how light travels, and how energy flows. Feynman stressed that physics does not answer why, in the philosophical sense. It answers how, with precision. Magnetism works not because it resembles something familiar, but because the universe obeys these mathematical rules consistently. This is deeply uncomfortable for the human mind. We evolved to understand pushes, pulls, and contact. We like causes we can picture. Magnetism refuses to cooperate. There is no tiny hook reaching out from one magnet to grab another. There is no stream flowing through space like wind. There is a field, an abstract entity defined by numbers at every point in space. The field is not made of matter, yet it carries energy and momentum. It can exist even in a vacuum where no particles are present. Magnetism, then, is not happening between objects in the ordinary sense. It is a feature of space itself as structured by electromagnetic laws. Feynman's point was not to strip away wonder, but to relocate it. The wonder is not that magnets pull each other, but that the universe can be described by a small set of principles that generate such behavior at all. When you hold a magnet, you are touching the visible edge of a deep, invisible order. You are feeling the collective consequence of quantum spins, electric charges, relativistic effects, and field interactions, all acting in harmony according to rules that do not care whether you understand them or not. This perspective shatters the comforting illusion that the world is built from simple, intuitive pieces. Magnetism reveals that what seems solid and obvious is often emergent and secondary. The real machinery of the universe operates at levels far removed from human experience. We can measure it, calculate it, and use it, but we cannot reduce it to everyday imagery without distortion. Feynman argued that accepting this limitation is not a failure of understanding but a mature form of it. To understand magnetism is not to imagine invisible hands pulling metal together, but to accept that nature's deepest explanations are mathematical and relational. Magnetism works because electric charges exist, because quantum rules govern their behavior, because fields fill space, and because these elements interact according to laws that have no deeper justification within physics itself. In this sense, magnetism becomes a lesson in intellectual humility. It teaches that reality is not obligated to make sense in human terms. The fact that magnetism is not a separate force, but an emergent aspect of electromagnetism, reminds us that the universe is unified in ways that defy common sense. What we experience as distinct phenomena are often just different faces of the same underlying structure. When Feynman said that magnetism is not really something on its own, he was not dismissing it. He was elevating it. He was showing that even the simplest objects on your desk are connected to the deepest laws of nature. A magnet is not just a tool or a toy. It is a doorway into quantum mechanics, relativity, and field theory. It is evidence that reality is layered, subtle, and far stranger than our instincts suggest. By following this keynote to its end, the question, "Why do magnets work?" transforms. It stops being a request for a comforting story and becomes an invitation to confront how the universe actually operates. Magnetism works not because of a hidden mechanism waiting to be visualized, but because the fabric of reality itself behaves in a particular, rule-governed way. And that realization, more than the attraction between two pieces of metal, is what truly reshapes how we see the world. Richard Feynman's second keynote idea cuts directly into one of the deepest habits of the human mind, the urge to keep asking why, until the universe finally gives a satisfying, mechanical answer. Feynman argued that this urge, while natural, eventually collides with a hard boundary. When you ask why magnets work, or why anything works, you are not guaranteed an explanation that feels intuitive or complete. At some point, science does not deliver a deeper cause in familiar terms. It delivers a fundamental law and stops. This idea is unsettling because it challenges how we believe understanding should feel. In everyday life, explanations usually end in something tangible. A door opens because you pushed it. A glass breaks because it fell. Fire burns because it is hot. These explanations work because they reduce unfamiliar events to familiar actions. When we carry this habit into physics, we expect the same structure. We want magnetism explained as tiny hooks, invisible strings, or some hidden machinery pushing and pulling behind the scenes. Feynman's point was that nature does not owe us that kind of explanation. He illustrated this brilliantly by imagining a conversation between a physicist and someone unfamiliar with science. If asked why magnets attract, the physicist might say, because of magnetic forces. But that is not an explanation, it is a renaming of the phenomenon. Pressed further, the physicist might mention fields, electrons, or quantum effects. Each step sounds more sophisticated, but the listener can always ask, why do those things behave that way? Eventually, the chain of explanations ends not with a picture, but with an equation. Feynman stressed that this is not a failure of physics. It is a misunderstanding of what physics is designed to do. Physics is not a catalog of ultimate causes in the philosophical sense. It is a framework for describing patterns in nature with precision. When we reach fundamental laws, we are not supposed to ask why in the same way anymore. The question itself stops making sense, because there is nothing deeper within the theory to point to. This clashes with our intuition because we confuse explanation with familiarity. We feel satisfied when an explanation connects a new idea to something we already know. But fundamental laws do not connect downward to simpler concepts. They are the simplest concepts available within that framework. Asking why they exist is like asking why the rules of chess are what they are. You can analyze their consequences endlessly, but there is no deeper rule within chess that explains the rules themselves. Feynman was careful to distinguish between two types of why. One is causal within a theory. Why does this object move that way? Because this force acts on it. That kind of why is meaningful and powerful. The other is ultimate. Why does this force exist at all? That question points beyond the theory, and physics has nothing to say there. Magnetism lives precisely at this boundary. You can explain how it behaves with extraordinary accuracy, but the moment you demand an ultimate cause, you have stepped outside what science can provide. This realization can feel disappointing at first. It seems to strip the universe of a final, comforting explanation. But Feynman argued that this disappointment comes from misplaced expectations. We expect nature to behave like a machine built by humans, where every part has a reason tied to human logic. In reality, nature behaves more like a mathematical structure that simply is the way it is. The laws are not justified, they are discovered. When applied to magnetism, this idea becomes particularly vivid. You can trace magnetic behavior back to electrons, their spin, and electromagnetic fields. You can unify electricity and magnetism into a single theory. You can even show how magnetism is connected to relativity, where motion changes how forces appear. But once you reach the equations that describe these relationships, there is nowhere else to go. The equations work. They predict experiments, they build technology, but they do not explain why the universe chose those equations. Feynman often warned against mistaking the depth of a question for its validity. A question can feel profound and still be unanswerable within a given framework. Asking why magnets work at a fundamental level is like asking why numbers obey arithmetic. The rules define the system. They are not consequences of something simpler inside the system itself. This perspective reframes what it means to understand something. Understanding magnetism does not mean being able to picture a mechanism that satisfies common sense. It means knowing the laws that govern magnetic phenomena and being able to use them reliably. Engineers who design electric motors do not need a philosophical justification for Maxwell's equations. They need the equations themselves and the confidence that they work every time. Feynman believed that confusion arises when people expect science to replace philosophy or theology. Science does not answer why the universe exists or why its laws are what they are. It answers how the universe behaves given those laws. When people ask why magnets work, they often unknowingly ask a philosophical question using scientific language. Feynman's answer was to gently but firmly separate these domains. This separation does not make science shallow. On the contrary, it reveals its power. The fact that a small set of laws can explain an enormous range of phenomena is astonishing. Magnetism, light, radio waves, and electric currents all emerge from the same underlying principles. The why of their unity is not explained, but the unity itself is real and testable. What truly unsettles people is that this means there is no hidden layer of reality waiting to restore intuition. There is no final picture where everything suddenly makes sense in everyday terms. The deepest level we currently know is abstract, mathematical, and resistant to visualization. Magnetism is not mysterious because it is complicated. It is mysterious because it is simple in a way that human intuition cannot grasp. Feynman argued that this realization should change how we ask questions. Instead of demanding ultimate reasons, we should ask what the rules are and how far they go. Instead of being frustrated that the universe does not explain itself, we should be amazed that it is explainable at all. Magnetism does not come with a story we can tell in ordinary language, but it comes with equations that work across galaxies and inside atoms. This also reshapes our sense of reality. If the deepest explanations stop at laws, then reality is not built on purpose or narrative, but on structure. Things happen not because they are meant to, but because the laws allow them to. Magnets attract not for a reason we can translate into human terms, but because the structure of the universe includes interactions that produce attraction under certain conditions. Feynman's insight here is not nihilistic, it is clarifying. It frees us from the endless, unsatisfying loop of asking why in the wrong way. It invites us to appreciate the universe on its own terms, not ours. When we accept that some questions end in laws, we stop feeling cheated and start seeing the elegance of the system. In this light, magnetism becomes more than a physical phenomenon. It becomes an example of how knowledge itself is structured. There is a surface level where things appear mysterious. There is a deeper level where patterns emerge. And there is a deepest level we can currently reach, where laws stand without explanation. Each level is meaningful, but none replaces the others. Feynman wanted people to understand that reaching a fundamental law is not a dead end. It is an achievement. It means you have gone as far as current human knowledge allows. The fact that magnetism ultimately rests on laws rather than causes is not a weakness of science. It is a reflection of how the universe is organized. When you hold two magnets and feel them pull together, the experience invites a simple question. But Feynman's answer transforms that question into a lesson about the limits of explanation itself. The universe does not answer every why with a story. Sometimes it answers with a rule and silence. And learning to live with that silence, without filling it with comforting but false images, is part of truly understanding reality. The third keynote centers on a statement that sounds simple but quietly overturns almost everything our instincts tell us. Magnetic attraction does not come from mysterious pulling, invisible glue, or some special magnetic substance. It comes from moving electric charges and a quantum property called spin. This idea feels technical at first, but if followed carefully, it dismantles the way we imagine forces acting in the world and replaces it with something far stranger and far more profound. When two magnets attract, the sensation feels direct and physical. You feel a pull in your hand, as if one object is reaching out across space to grab another. For most of human history, this feeling encouraged magical explanations. Magnets were thought to possess hidden spirits or special essences. Even today, many people subconsciously imagine magnetism as a unique force that exists alongside gravity, electricity, and friction, each operating independently. Feynman argued that this intuition is wrong at its core. At the deepest level, there is no such thing as a magnetic pull in isolation. What exists are electric charges and the rules that govern how they behave when they move. Electricity and magnetism are not siblings. They are the same phenomenon seen from different conditions. Magnetism is what electric forces look like when charges are in motion and when quantum effects dominate. To understand why this matters, consider electricity first. Electric forces arise from electric charge. A charged particle creates an electric field around it, and other charges respond to that field. This idea, while already abstract, still fits somewhat into intuition. We can imagine charge as a property objects carry, and the field as an invisible influence filling space. But magnetism enters the picture when charges start moving. When an electric charge moves, it does not merely create an electric field, it also creates a magnetic field. This magnetic field affects other moving charges. The key point is that magnetism depends on motion. If all charges were perfectly still, magnetism, as we know it, would not exist. This alone should shake intuition. A force that depends on motion is not a basic push or pull in the everyday sense. It is conditional, relational, and deeply tied to how observers move relative to one another. Inside a magnet, electrons are constantly in motion. They orbit atomic nuclei, and, more importantly, they possess spin. Spin is one of the most misunderstood ideas in physics, because the word itself invites the wrong mental image. Electrons are not tiny spheres spinning like planets or tops. Spin is a purely quantum property. It has no exact counterpart in classical physics. Yet, mathematically, it behaves as if the electron carries a tiny magnetic moment, like a miniature bar magnet. In most materials, these tiny magnetic moments point in random directions. Their effects cancel out, and the material shows no noticeable magnetism. But in certain materials, like iron, the interactions between electrons cause many spins to align in the same direction over large regions. When this happens, their individual magnetic effects add together. The result is a macroscopic magnetic field strong enough to move objects you can see and touch. This explanation already departs radically from everyday intuition. Magnetism is not caused by one object reaching out to another. It is caused by the collective behavior of countless electrons obeying quantum rules. The force you feel is not localized in a single place. It is distributed across fields that exist throughout space. When a magnet attracts a piece of iron, the electrons inside the iron rearrange their spins in response to the magnetic field. The attraction is mutual and dynamic, not a one-way pull. Feynman emphasized that this rearrangement happens without any physical contact in the ordinary sense. Nothing travels from the magnet to the iron like a rope being thrown. Instead, the magnetic field influences how charges move and align. The field itself is not a substance. It is a mathematical description of how forces would act at every point in space if a charge were placed there. This leads to one of the most unsettling ideas in physics. Forces do not require physical contact or material carriers. Magnetism operates through empty space, yet it is not correct to think of space as empty. Space is structured by fields. These fields store energy, transmit influence, and respond to changes. In this sense, magnetism is not happening between objects, it is happening everywhere at once, guided by rules that assign values to every location in space. The role of relativity deepens this strangeness. According to Einstein's theory, electric and magnetic fields are different aspects of a single electromagnetic field. What appears as a magnetic force in one frame of reference may appear partly as an electric force in another. Two observers moving relative to each other can disagree on the balance between electric and magnetic effects, yet both will predict the same physical outcome. This means magnetism is not an absolute feature of reality. It depends on motion and perspective. Feynman loved pointing out how disturbing this is for common sense. If magnetism depends on relative motion, then it is not a fundamental thing, in the way we imagine solid objects or fixed forces. It is an emergent description that arises when charges move and observers compare measurements. Magnetism is real, but its reality is subtle. It is real in the way patterns are real, not in the way bricks are real. The idea that magnetism comes from moving charges also explains why magnetism and electricity are so deeply intertwined in technology. Electric currents produce magnetic fields. Changing magnetic fields produce electric currents. This is not a coincidence or a clever engineering trick. It is a direct consequence of the underlying unity of electromagnetism. Motors, generators, transformers, and wireless communication all exist because electric and magnetic effects are two faces of the same interaction. Yet even this powerful unification does not restore intuitive comfort. Saying that magnetism comes from moving charges only pushes the question back one step. Why do charges behave the way they do? Why do electrons have spin? Why do the equations describing electromagnetic fields have the form they do? Feynman's point was not to answer these questions, but to show that magnetism loses its air of mystery only to reveal a deeper, more abstract one. What shatters reality for many people is realizing that there is no hidden mechanical picture underneath all this. There are no gears, no tiny springs, no microscopic hooks. The universe does not operate like a machine built from familiar parts. It operates according to rules that are mathematical at their core. These rules describe relationships, symmetries, and transformations, not physical objects moving in intuitive ways. Magnetic attraction, then, is not a fundamental action. It is a visible consequence of deeper rules playing out on a massive scale. When you feel a magnet pull, you are feeling the end result of quantum spins aligning, electric charges interacting, and fields responding across space. You are not feeling a cause, you are feeling a pattern. Feynman often stressed that trying to picture this process using everyday imagery is not just difficult, but misleading. Any picture you draw in your mind will inevitably smuggle in assumptions from the macroscopic world that do not apply at the quantum level. Electrons are not little balls, fields are not fluids, forces are not pushes. The true explanation lies in equations that resist visualization.